Tell me what happened, okay?
Okay. Well, she took 2 pieces of my bread.
She did?
Yeah.
Did she ask for them?
No.
No?
No, she just grabbed them.
Did you grab her bread, Sadie?
No.
No.
Yeah, she really did.
She said she didn't take your bread.
But she did.
Sadie, did you take her bread?
No. She's lying.
She is?
Yeah. She took my bread.
What's in her mouth?
Bread? My bread.
What's in her mouth?
My bread.
Oh.
She already took the other piece. All of it. And she already ate all of it. Again.
Sadie, was that bread good?
Yeah.
Do you want to say sorry for taking Addie's bread?
Sorry.
Okay. You want to give Addie a kiss? Come give her a kiss.
I forgive you.
Good morning to everybody. Welcome. We can start the lesson of today. So just sharing my screen. Okay. We were talking about, I remember to you, ODS materials. So let's go on. ODS materials are first of all fabricated in form of powders. Then the powders must be consolidated, and for this we have available the fabrication technologies which are classified under the class of powder metallurgy techniques. What means that they are fabricated first of all as powders? That we need something to dissolve one material in another material, starting from powders of these two separate materials, in order to achieve two, let me say, objectives. The first is the average size of the fabricated final powder, which must be suitable for using with powder metallurgy techniques. And here we are talking about something which has an average diameter of 10 tenths, sorry, I mean 30, 40, 50 micrometers. And the second aim that we want to reach is to dissolve one material in another one compound in another one, that depends on the starting materials, in order to force or to have a solid solution. Thus, the final results of this pre-step, we could say, is the fabrication of powders having a suitable granulometry distribution, that is a suitable size of average diameter, and being composed of at least two different materials, that is an alloy. In our case, obviously, if we want to specialize this process for the fabrication of oxide dispersion strengthened materials, we need to start with a metallic alloy powders, with a ceramic powders, and then we have to perform the solid solution and the final fabrication of the alloyed powders. And this is made by using a mill. In order to achieve both, let me say, our aims, milling and alloying. And so these techniques put together are called mechanical milling and mechanical alloying. And the milling methods that we know that we have available are essentially two. The first one is based on the use of a planetary mill. The second one is based on the use of an attrital mill. The second, that is the attrital mill, for the reasons that I will tell to you in a moment, is the most suitable and is the one used in order to fabricate the powers we are talking about. The planetary mills are very diffused, very used, but for small-scale research and development activities because they usually can treat at maximum 1 kilogram of total materials. And in a planetary mill, each vial, which contains mild steel balls, rotates on its own axis around a rotating disc having a support function. So the centrifugal forces which arises, they are able to cause the grinding balls travel across the vial, collide on the opposite wall, and thus giving origin to welding between powders, fracturing of the same powders, cold working of the powders, and alloying if we are going to use two different types of powders. Instead, the Triton mills, they do have a very higher capacity from 1 to 50 kilograms, and so they can be proposed and they are used, let me say, for our purpose when we want to have amount of powders which can be used for fabrication of real engineering components and components having engineering size. In this case, the difference is related to the fact that each vial, it contains vertical impellers that energize the ball, which are inside vial, and then impact with other balls, container balls, and powders put inside give rise to milling and give rise also to alloy. This is a most, let me say, more effective methods to get milling, to get alloying for the quantities of materials which have meaning from an industrial point of view. And so the Triton mill is the techniques, I would say, the equipment better, which is used to get alloying and milling. So what is going to happen if we make this question, if we, let me say, put our attention on the milling time, that is on how much time we are going to use the mill with powders inside. Qualitatively speaking, because obviously every system has its own figures, its own number, what is going to happen is, and we will give an explanation of this, we will have, by increasing the milling time, a decrease in the average final particle size. And this phenomena is not an infinite phenomena. I mean, we do reach a sort of equilibrium in terms of final average diameter of the milled and alloyed powders after a certain plateau for what it concerns the milling time. So if our aim is to get a final predefined distribution, let me say, we need to understand if the milling we have in front of us is able to get that final granulometry of the powders, because it is not true that if we increase indefinitely the milling time, we are able to get always particles having a decrease or a decreasing dimension. Why this is going to happen? Because we do have, at the same time, looking to, let me say, mechanical interaction between the balls, which are inside the vials, and the powders, which are put inside the powder, the vial. We do have two phenomena. The first phenomena is related to impact of balls with the feeded powders inside the mills. Impact, that is an impulsive load. So this is able to break the powders and thus to make to the powders an effect of cold work hardening. So we have cold work hardening and we have a fracture of the powders. And this is an effect which has as results, since we are going to break the powders due to impact, a decrease in the average size of the original powders. But at the same time, when we break a powder, we are going to expose polished surfaces of the powders itself. And then with other impacts, which put together polished surfaces, welding phenomena can occur. So we have two phenomena. The welding one, which is responsible, if considered alone, of an increase in the average diameter of the final powder, and the breaking due to impact called working strain hardening of the materials itself, which is responsible of a decrease in the final average diameter of the powder itself. When these two effects, which give results one in the opposite of the other, they balance among them, between them, we have reached, let me say, the plateau of the milling time. And this is the reason because we have this kind of qualitative behavior in terms of reduction of particle size, if referred obviously to the original particle size. There is also another interesting effect due to the balancing of these two phenomena related to the fact that if you are going to look the final average distribution of diameter of the powders produced with this technology, that is, we are going to, let me say, have a look to the granulometry, like in these figures, these diagrams of the produced powders, we do have a very sort of narrow distribution. So most of the diameters of the final powders obtained, they are near an average size. We can also expect a sort of normal or Gaussian distribution, which is very narrow. And this is very interesting and very important because of when we think to use this raw change if we are going to increase the milling time. So it is not going to change after the plateau the average final diameter of the fabricated powders. But if we, as in our case, are thinking to use two different powders, for example, like in this picture, the white one and the black one, we can have a sort of layered structures inside the single powders for which the thickness by material one, then we have another layer of the second materials, then we have another layer of the fourth materials, and so on, are going to be reduced by increasing the milling time. So the average size does not decrease because we have reached the plateau here, but the thickness, in the case we are going to use two different materials of the single layer, are going to be decreased. And so the microstructure of the final particles produced in this way, alloyed, produced in this way, is going to be more and more refined. And this can allow us, for example, also to have nano-sized oxide particles dispersed inside a metallic matrix, which is nano or submicron. But that means, as we said some time ago, less than 100 nanometer or less than more or less 500 nanometers, which represent the starting point for obtaining suitable ODS powders, materials, which can then be consolidated. This technology of building an alloy can be used not only, generally speaking, for the fabrication of ODS powders, but it can be used also for the fabrication of nanostructured materials, again, starting from powders, okay, so nanostructured powder materials, we should say. And then, since we can also force more than the equilibrium state for what it concerns solid solution, we can also obtain Sora-saturated solid solution, metastable alloys, and so it is important for, again, non-conventional materials. But please remember that we are introducing, in terms of fabrication technology, an intermediate steps, in the sense that we are going, first of all, to fabricate this kind of materials in powder form, by MM or by MA, mechanical milling or mechanical alloying, and then we need to use a consolidation technology, which is usually inside the area of the powder metallurgy technologies, on which we will say later on something to be, let me say, more concrete. This is a table in which we can see, so generally speaking, we can make also a general approach to this technology of mechanical milling and mechanical alloying, which kind of materials have been fabricated in terms of powders with these techniques. So you see, in addition to ABS alloys, and here we will say something in the other next slides, also light alloys or metal matrix composites or intermetallic materials or metalloceramic materials, the one which are called ceramic materials, metastable systems, nanocrystalline materials, and other ones not used for let me say structural applications like superconductors and magnetic materials. And now we will see later let me say powder metallurgy technologies are more or less the most important technology for the fabrication of high coercivity magnetic materials based on neodymium, iron, and boron. So it's a sort of version of, let me say, techniques, this one, which has a broad range of possible applications, not only for the fabrication of ODS alloys, but also for the fabrication of these other class, which have been tested and which have been fabricated then also in the form of final component. We are interested in this. We are interested because we are talking about ODS for high temperature applications in nickel-based superalloys, typically nickel with titanium superalloys, in which ceramic particles are dispersed inside, and these are essentially the definition of an ODS materials according to our interest. Which are these ceramic particles? In most of cases, I would say in the majority of cases, they are essentially yttria, that is yttrium oxide. So in order to have a mechanical alloy with this purpose, we need to put inside our mill yttrium oxide powders and a nickel-based superalloy powders, and then we have all the two mechanisms that we have described before, that is alloying and definition, let me say in this way, of the final and average diameter of the alloyed powders. This is one example of powders. The resolution, that's an optical microscopy, does not allow to us, but we will have another picture to see how inside this wide area, which is essentially the metallic part of the finally fabricated powder, others, we do have dispersed ceramic particles inside in a very uniform way. And so these are interesting. Why? Because we expect, but we will have to see something more, that these kind of materials, due to, as we said last time, the fact that a part of these materials is already an oxide, because we have dispersed oxide inside, it can show higher stability to higher working temperature. And this is true, also with some benefits, but it depends on the working condition for what it concerns the creep resistance. Why some benefits for what it concerns creep resistance? Because if, and I want to underline if, we are able to disperse an oxide phase inside a metallic matrix, like in this case, but the oxide phase must have a very, very low dimension, a very, very low size, because it must be able to be considered not as an inclusion, but as a second phase, able to interact with dislocation movements. We can remember that the dislocation movement, as we already said, but we can repeat it, are, let me say, made more slow due to the fact that if a dislocation match a non-metallic phase, it cannot move inside the non-metallic phase, but it must activate the climb or closed sleep mechanism, depends on the dislocation type, in order to travel around these low energy obstacles. And this means that the dislocation movement is made more difficult, and means that we can expect an improvement in terms of resistance of the materials itself to power low dislocation based creep. Remember, but we must remember that this kind of creep is not the only one existing. We do have also the diffusion creep, for which we do have, let me say, the possibility to contrast the permanent deformation due to diffusion creep by using the single crystal technology. Well, the single crystal technology cannot be used in this case with ODS materials, can be just used with the already known nickel-based approach, nickel-based superalloy, I mean, with controlled solidification. So at a glance, overall, speaking in terms of a sum of these two phenomena, today still the nickel-based known superalloys, they do have a better creep resistance of the ODS materials, because we can act on both creep phenomena, diffusion and dislocation-based creep. Since instead with the ODS materials, we can just act against the dislocation creep, but not against the diffusion creep. And this is the reason, because we can expect a better behavior in terms of higher working temperature, but as we said last time, a lower overall, let me say, resistance when we include in our application the possibility of the existence not only of the dislocation-based creep, but also the diffusion-based creep. These are some of the most known alloys, let's say superalloys, which are used for the fabrication of ODS materials. As I told to you, if we have a look now to this picture on the upper right corner of the slide, we can see the black dots here. You see these black dots are the yttria, ceramic particles, which are dispersed inside the metallic matrix. And if we have a look to this table, we can see that essentially there are two classes of superalloys which are used, or have been used, but I would say are used for the fabrication of ODS materials: iron-based where you find balance here, that means that it's an iron-based superalloys, or nickel-based, when you find balance in the column of nickel, that means that nickel-based superalloys. You see here, you see in the column of the ceramic type, which is used to fabricate the ODS, that we all in all these cases we do have yttrium oxide, also called yttria materials. And these are also, let me say, the classification in terms as the designation of the ODS alloys, which do not have any correspondence, like in other cases, with chemical composition or with mechanical properties. Just the first two letters MA, it means mechanical alloyed, or the first two letters PM means that they are powders used for powder metallurgy technology in order to have the final, let me say, components. So we have also a panorama of the most common ODS powders which can be found on the market. The application, we already said something about the possibility, or let me say the interest in aerospace, in automotive, in power generation, in furnace furnitures. But if we go to our purpose, let me say we need to specify this. We need to specify that nickel-based superalloys, which belong to the ODS class, can be classified according to the quantity of aluminum and titanium which are present as alloying element. And we can have high aluminum and high titanium, or low aluminum and low titanium. The one which contains low content of aluminum and titanium, they cannot be strengthened with a gamma prime phases that we studied when we talked about generally superalloy, nickel-based superalloy materials. But nevertheless, the presence of chromium, for example, and of aluminum itself, it can improve the oxidation resistance, as we said before. With a higher aluminum and titanium concentration, we have the possibility to have the double phase gamma prime, so we can rely on an important mechanism for what it concerns the additional obstacles for dislocation movements. But again, I say to you that the possibility to have a single crystal alloys is not possible in the first, neither in the second case. So we can be oriented, that's the, let's say, sort of final conclusion on the use of ODS materials eventually in engines when we want to look into this conclusion, when we want to increase the oxidation resistance of the materials itself. But this, what does it mean? That we are thinking about higher working temperature. But this, what does it mean? It means that if we are working, we are thinking about higher working temperature, we are thinking about working condition in which, remember, diffusion creep is very important. Not only creep based on dislocation movement, and thus we can say that nowadays, due to the fact of the possibility offered by simple nickel-based superalloys to have a single crystal fabrication technology not offered by ODS alloys, still the nickel-based superalloys are the most important materials for high-performing turbine blades very, very stressed instead of ODS. ODS, nevertheless, they have found, and now we are talking about practical application, other let me say, fields due to their properties of higher resistance to temperature. In these cases, most of them are not nickel-based superalloys, but they are iron-based superalloys. Here you have some examples in which also nickel-based superalloys are included. For example, pre-oxidized weldless Barnett tubes, or honeycomb, or Barnett nozzles, or guide vanes, which are made of powders. You see the classification PM, which are reported here in the slide that I have already shown to you. This is a combination of iron and nickel base. Just to give to you the idea that some applications, they do exist also for the nickel-based ODS superalloy, but not in the field of essentially of blades. The sectors for which the ODS are actually very, let me say, interesting and important are different from our sectors, because they are essentially two. The first is related to nuclear applications, for the fabrication of pipes, these tubes of ODS ferritic steel, for liquid sodium cooled fast reactor. And we here, let me say, can give benefits on the improved creep resistance, but you see the temperature is not the temperature for which we can expect a very, let me say, consistent diffusion creep. Or for heat exchangers, high temperature heat exchangers where oxidation phenomena can, let me say, damage the metallic alloys, can have benefit by the fact that inside the metallic alloys, iron-based, also in this case, we will disperse oxide particles, so and thus reducing the overall oxidation, deterioration of the materials itself. Still remains some problems which limit the overall application of this kind of materials, apart from the field that we already have discussed of the blades, related to difficulty in joining. And thus, let me say, not very, there is some activities and development, but this is a sort of intrinsic limitation of an ODS materials due to the fact that joining classical joining techniques are obviously not suitable when we do have ceramic phases inside the materials inside the materials. But the interest in these alloys still is active and remains, is real for energy sector, heat exchanger, and nuclear applications. So we have seen, let me say, and we have mentioned many times during this discussion, the powder metallurgy processes. And I want to discuss a little bit with you. We will not be able to finish today, so we will finish in the lesson of next Monday. What does it mean, better powder metallurgy? Because when we talk about, and we are now, even though it is used also in other sectors, but we are now, let me say, confining this discussion to metallic alloys. When we talk about the fabrication of components, engineering components made by metallic materials, we have already said that we have always said that we do have two main classes of technology. The first one is the casting technology that implies melting and solidification of the alloys inside the die, having, for example, an edge-shape size. And the second one is the possibility to start from raw materials, again obtained, but not with the final shape, with casting technology, but using plastic deformation techniques in order to give the final shape and size that we want, like, for example, rolling, like, for example, extrusion, like, for example, laminates and lamination and so on. All these two classes of processes, one start from a liquid phase, and the second one start from a solid phase, which is then the default. But in the solid phase, in the second possibility, that is the plastic deformation, we do have bulk materials. Now we have discussed about mechanical milling and mechanical alloying, and the results of the mechanical milling and mechanical alloying is not a good thing to use these powders as, let me say, raw casting materials. I mean, I have my alloyed powders, then I melt these powders, and then I use a classical, let me say, casting technology. Obviously, I cannot think to rely on plastic deformation when we start from powders. But if we have alloyed powders, when we have alloyed powders, and especially in the case we have alloyed powders, for example, with a second phase, which is a ceramic phase, we cannot expect to obtain good results if we melt the powders and then let the powders to solidify. Because the ceramic phase, which is more light than the metallic phase, the metallic base alloys, will not more retain if put in a liquid phase its homogeneous distribution. Then it can also experience, that depends on the starting powder's grain growth, but that's another matter. And so we need to, we are not able to, we cannot to melt the ceramic phase, because if you are going to think, for example, to zirconia, just to mention another ceramic materials with a nickel-based superalloys, zirconia melting temperature is around 2,700 Celsius. The nickel-based superalloys melting temperature is something around 1,500 Celsius. So we should reach, in order to melt the zirconia phase, at least 2,800 Celsius. And you can understand that this is not possible. We already met these problems when we talked about some years ago ceramic materials, and we introduced at that time another important fabrication technology, which is based on the sintering phenomenon. And I remember to you that sintering phenomena, generally speaking, and we can add also some variants like reaction sintering or liquid assisted sintering, but generally speaking, when we talk about sintering, we are not thinking to the presence of liquid phases. And we start essentially from powders. Then we put these powders into a mold with a certain procedure. We give to these powders energy, for example, thermal energy, that is temperature. Then we can apply also force. And this has as result that solid state diffusion can give rise to the fabrication, to the development of a three-dimensional bulk structure due to solid state diffusion. And so the powder metallurgy technologies, even though we are talking about metallic or ceramic metallic alloys, are based on sintering. Also them are based on sintering starting from powders. So we need as our raw materials powders, and then we need to let the sintering phenomenology to happen in order to have the consolidation of the powders and in order to have the fabrication of the final component. So the powder metallurgy is a branch of the science and material science and technology and metallurgy, which generally speaking can be referred to the fabrication of powders or to the fabrication of components. It's very interesting also, perhaps you can appreciate this picture, the possibility to strictly control the consolidation phase, in the sense that starting from powders, we could stop when we want the consolidation phase due to solid state diffusion, having a controlled, also high residual porosity inside the materials itself. And this, for example, can allow to us to control the porosity, which is an essential feature for components like, for example, lubricated bearings, because we can put inside these voids, because they are essentially voids, in the sense that no materials is inside, a solid state lubricant. Let's go on. The powders are not only used, just to complete the introduction, are not only used for metallic powders, for powder metallurgy, but they are actually, technically, engineering speaking, used also as raw materials without needs of sintering to fabricate the final component. For example, we have metal powders, just some examples, metal powders which are used in organic-based brake pads, and they act as friction modifiers. The content is not so high, some percent, from 5 to 10%, and they can give rise to a very important effect, which is the stabilization of the friction coefficient, especially during the so-called fade behavior of the material itself. That is what is going to be developed when you are braking a lot, and that is you get and you reach a high temperature on braking pads. Or we have powders which are used as metallic flakes, for example, based on aluminum, in the metallic paints for cars, to give an appealing look, as well as in other applications, like paints. Or powders are also used alone as fireworks and for explosive. In this case, we have reactive metals such as magnesium, aluminium, titanium, which are used in the formulation, directly in the formulation as powders, and they must remain powders to give their effect in the formulation of explosives and fireworks. Or we can have also powders like flakes based on copper, nickel, silver, for example, which are dispersed into polymeric-based pastes in order to have a conductive behavior of the final materials. And this is another application of powders without any sintering phenomena, as well as in the case of permafrost cooling with heat pipes. So we do have application, that's the message of metallic powders, also, if you want, fabricated by mechanical building and mechanical alloying, not only for sintering, but also for other fields where powders, they are used as they are. But for the fabrication of the component we have in mind, we need to rely on sintering, and that is, we need to rely on powder metallurgy. The powder metallurgy, let me say, had a great impulse, great development. This is a very brief history after the Second World War, and essentially to develop modified iron powders. And then the field was, let me say, increased in terms of interest and application even due to the development, in addition to the mechanical building and mechanical alloying of other technologies available at industrial level to fabricate powders, not only with MM or MA, but also with other systems like one we showed to you very shortly, which is cited here on this slide, and which is called water atomization, which are the steps of a powder metallurgy process. And I think that on these slides we can conclude the discussion of today. Then we will go on next Monday. Essentially, we have 4 steps, 4 phases. First one, we need obviously the starting powders. Then we have to mix these powders. And here we do have technologies for powder production and technologies for, let me say, mixing. Well, let us understand. We can put inside the step of powder production the possibility to use a mechanical milling or a mechanical alloying, or like mentioned here, a water atomization or a spray atomization process. Or we can also think that these technologies I mentioned to you are, let me say, representative of what is called here mixing, and these are the initial starting powders, just the same. But the concept is that we need to, especially if we want to have alloys, to have a 4th phase in which the powders are alloyed or mixed. Then they are pre-compacted, and also here, as we will see, we have different possibilities. In order to, let me say, have something which fabricate something which is very, very similar to the final component that we want to obtain. Here, the compaction can be made also by using a band, for example. That depends on the starting powders. But there is the formation of the same concept that we already have seen some years ago for the ceramic materials, a sort of green body. Okay? Then this green body, which has some, but very low, let me say, mechanical resistance, but it has some mechanical resistance, some consistency. After compaction, that is after application of a force, for example, in some cases can be tooled, must be put in a high temperature environment, for example, in a furnace, in which we can also decide to apply together with a thermal cycle, a mechanical cycle, and this is the, let me say, possibility, for example, which is represented by the so-called hot isostatic pressing. And it is in this phase, in the phase of high temperature presence, eventually assisted by a mechanical force, that is by pressure, that the single powders which have been mixed or which are alloyed powders start to develop the 3D network by sintering, by solid state diffusion, and after controlling the processing parameters, which depends on the final results we want to obtain. If we want to obtain a porous structure, or if you want to obtain a dense structure, depending also on the material type that we have at the beginning, which allow to us to predefine which are the temperature value, the time, and eventually the pressure which must be applied. We have the fabrication of the final component. And what is very relevant for this kind of technology is that, as you see here, even though this is a scheme, we do not have any liquid phase, first of all. Secondly, we get the fabrication of the component, which is always a net-shape fabrication. I mean, the compaction and then the sintering phase give rise at the final part, the final phase of this process, to the final component that we want to fabricate without, apart from polishing, any additional tooling phases to realize and to get the final shape and size. So this is, let me say, an overview of a powder metallurgy cycle, we could say in this way. Together with the mechanical processes we have already defined before, mechanical milling, mechanical alloying, we do have also other, as I told to you, possibilities to fabricate powders by means of physical processes, water atomization or gas atomization, sometimes also by using chemical-based or electrochemical-based technology, the so-called reduction processes. Of these three classes, the most important are the atomization and the mechanical milling process. So we have already seen the milling and alloying by using the technology we have defined for the ODS materials. We need to say a few words about atomization, water or gas, but this will be the start of the lessons of next Monday. And for today, it's all. So if you have questions, please. Okay, I do not see questions on your side. So have a good weekend and see you on next Monday. Bye bye to all.